One of the classic energy problems involves a child going back and forth on a swing set. And you'll see one probably on the test, the MCAS, and they'll ask you questions about where she has how much energy and how energy changes. We'll deal here just with how much energy she has at different places, uh, points A, B, and C. Now, we'll start with an assumption, two really, because there's no friction here in the swing set. That pressing up here, and a bigger one, there's no air resistance. In the real world, you would feel some wind. She'd feel wind in her face, wouldn't she? And that would slow her down some. But we will not assume that. We'll assume there's none of that friction, and so she'll go back and forth forever, basically, at as high as 2.5 on the top. That's how high she'll be. And on the bottom, she'll be at 1.3 meters forever. Now another question. What is the velocity of the girl at points A and C? A is at the top, and so is C. Think about this. She's swinging along here. She's climbing. She's going slower and slower and slower. Doesn't she turn around then? That means she has to be stationary at the very top. Just for a moment, she won't be moving at all. That means velocity will be 0 meters per second. Now that'll help us out with our kinetic energy numbers, I think. So does this make sense to you? Since we have V here in our kinetic energy formula, which is 0 here, then kinetic energy is also 0. Make sense? Happens over here too, doesn't it? She stops here as well. Velocity is 0, kinetic energy is 0. Now, I'm not going to get into calculating how fast she's going here in this video. Let's say she's definitely moving here down here, isn't she, B? In fact, wouldn't you agree that she's going the fastest? Yes. Velocity is the fastest. So I'm not going to get into how much kinetic energy she has but at this point, but that's the maximum, isn't it? That's where she has the most. Make sure you write down your video code here before we go on. All right, now we have KEs in here. Let's add our potential energies in here next as best we can. Now we know she's 2.5 meters above the ground here, don't we? So we definitely have potential energy because it has H in it. So let's see. For potential energy, we'll go mass of 60 times G is always 10, correct? Her height is 2.5, and that gives us 1,500 joules of potential energy. And since mechanical is kinetic energy plus PE, there 0 plus that number there is 1,500 for mechanical energy as well at the tops. She also goes to 2.5 height over here, so it's exactly the same here, isn't it? Again, with our assumptions, she's still reaching that height, 2.5. Good, same situation here, 0 kinetic, 1,500 potential, and 1,500 for mechanical. Now at the bottom, it's a little more sketchy here, because again, I'm not going to calculate the velocity, but we know kinetic energy is here, it's its maximum. But we're not at the bottom, are we? So we still have some height. So P is actually 60 times 10 by that 1.3, isn't it? So she still has some potential energy. It turned out she has 780. All right, so what's happening here then? She's going back and forth, and her kinetic and her potential are changing, aren't they? Look at this, 0 kinetic, all potential. That's the max, by the way, right? Maximum potential. Down here, she has plenty of kinetic. Her potential's gone down. Up here, she goes back to a situation where she has maximum potential energy, same mechanical. So back and forth she goes. And what we see here is kinetic energy transforming to potential energy and back and forth. But I'll discuss that more in a future video. For now, we're just satisfy ourselves to know we have no kinetic here, a bunch of potential. A bunch of kinetic here, less potential. No kinetic, and a bunch of potential here. And that's it for this video. Bye.